Okay. Okay, thank you.
So after class.
Okay. Yeah. Okay, thank you.
Is it okay like this? Okay. I think instead of horizontal. Yeah. Okay. Any question from yesterday? Okay. The clock. Okay, yesterday, I need to recap something. Yesterday I changed this word to above, right? Actually, this sentence means each leading entry of a row in a column to the right of the leading, in a column. Okay, try again. So each leading entry of a row is in a column the right of the leading entry of the row above it. Okay, so it says that every leading entry is on the right of the is in a column that's to the right of the leading entry of the row above it. Okay, so you will have something like this, so that you got a step line. Okay. Yeah. Yesterday I think I say something wrong. Any question on this row reducing, row echelon form? Okay, we will see again in the lecture soon. Okay. Let's recap what we did yesterday, and then we will talk about the linear combination again. Okay, because it's a quite important step. So recap what we did yesterday. Yesterday we looked at linear equation. So if you have two variable, okay, it traces out a line. Trace out a line in R2. Right. X. Okay. If you have three variables in your equation, it will trace out a plane in three-dimensional. Okay. So how should I draw the plane? Maybe I draw something like this. Okay. In general, higher dimensional, you will trace out a we call a hypersurface in R2. Okay, so in general, linear equation in n variables trace out a hypersurface in R. Okay. The most important thing is you have to keep in mind when you see a linear equation, you can trace out a surface. Okay, what surface? In low dimension, you can think of a line or a plane. Okay, and then what we do is we consider more than one linear equation, and then look at their intersection. Right. So if we look at, so we the goal is to find solution set that satisfy linear equation. Okay. So in geometry, we'll see how they intersect to give the solution. But in the linear algebra, what we do, okay? Yesterday, what we do is we have a linear of system equation. Linear of system equation, or I just call it linear system. And then we can transform it into augmented matrix. And we also can transfer it into a vector so that we can have this tree triangle here. So to remind you, we got an example from last time. For example, if we want to solve y equal to x and y equal to, for example, 2x plus 1 together, okay? We can write it in the form of linear equation, which is y minus x equal to constant, and then y equal minus 2x equal to constant, okay? And then from here, we can obtain the augmented matrix. Okay, and then how to transfer to vector equation? So we can write y times 1, 1, and then time minus 1 minus 2 equal to 0. Okay, so solving all this equation is the same. Okay, just different interpretation. Okay, so if I write in the imagine there's another geometry here. Okay, and yesterday we stopped at the matrix equation. Okay, so we define the matrix vector products to be this linear combination. Right. So in your mind, these four, you need to make sense why they are the same. Okay, these four things is solving the same solution. Okay, different way to looking at the linear system. Okay, so you need to keep in mind these four things is the same. So the question might change the way. All of them can use the same method to solve it. Okay. So, okay, let's remind us the matrix vector multiplication again. Okay, so let me change. Okay, so let's remind us again the definition of matrix vector multiplication. Okay, so how do you multiply a matrix and a vector together? Okay. So vaguely is defined be the linear combination. So remember what's the linear combination? What kind of operation you can do? There are two operations you can do in this linear combination. You can do scalar multiplication. You can do vector addition. Okay. So how do you combine the two numbers here? Okay, two objects here. So first you split your matrix into columns, okay, and then you split your vectors into scalar, okay, and then you take the linear combination of the column of matrix multiplied by the corresponding scalar of the in the vector. What I mean by that? So in the mathematical form, so you have a matrix, you split them into columns first, okay, and then you split your vectors into scalar or numbers. And then you need to make sure that the number of column and the number of scalar in the vectors matches up so that you can pair one of them to each other. Okay, make sense? Okay. So in the end, what you get is AX is equal to X1 A1 hat plus X2 A2 hat all the way to X. So you see that I use N here. Okay. So N can be anything 1, 2, 3, 4, 5, 6, 7, 8. Okay. You can imagine one of them. So if you are really interested, right, you can go to my website. Last semester, I got the discrete math lecture notes. You can read about the logic part and the set theory if you want to know about this notation more. Okay. Okay. And then, okay. So what does this mean? So this is the matrix vector multiplication is the linear combination. Okay. It's linear because there's no square involved in the vector. And is a scalar multiple of the column from the matrix and multiplied by the scalar obtained from the vectors. Okay. Uh, Before we talk about this theorem here, we should remind us another definition first. Okay, so why you might ask why we care about this form, right? Okay, so the good thing about this form is if AS bar equal to B bar, B hat or B arrow has a solution if and only if V bar is a linear combination of the columns of A. So if you can find, right? So if you can find x1 up to xn such that it equals to B hat, then you can then it means it has a solution. Okay, because you can solve this variable. And so in general, we can define a linear combination of a set of vectors. Okay, find the linear combination set of vectors. Okay, so how do we define this? So a vector y equals to c1 v1 hat plus c and vn hat, where c1 ci's are scalars, is a linear combination So, for example, what? Okay, for example, what is it? So u plus v, u minus v, and 0, and u are all linear combination of. Okay. So when we talk about linear combination, right? So we need to start with some vectors, okay? Maybe you got 3 vectors, and how you combine these 3 vectors, you can only add them and scalar multiply them, okay? These are the 2 operations you can do, okay? And all the operations you can do, they are called the linear. The vector you produce are called the linear combination, okay? So you combine, okay? You combine the vectors linearly, okay? You combine the vectors linearly. Okay, so this is the linear combination. So since you can have such different way to do linear combination, so we can collect all these combination together, and we call it a span. Okay, so we call it a span. So we collect all the linear combination together, and this set we will call it a span. It's called span of V1 up to N. Okay, so maybe let me show you some magic. Okay, maybe you don't believe, or maybe you can't picture this. So let's talk about R2. Okay, let's talk about R2. Yesterday we said, how can we write R2? Anyone remember how can we write R2? The vector in R2? Anyone remember? How do we write vectors in R2? I remember, cannot remember. Okay, so R vectors in R2 represented by an arrow from the origin. Okay, so how you record this arrow? You just take the endpoint. Okay, you just take the endpoint. Then this will specify all the information for the vectors. Okay, so a vector in R2 will be written by the square brackets v1, v2. Okay, so the claim is R2, this vector is a linear combination of 2 vectors. Okay, so can you guess what's 2? Maybe the obvious one. Okay, so the claim is every vector can be written as a linear combination of 1, 0, and 0, 1. Okay, so okay, from this equation here, it looks true, right? Okay, because when you expand this part out, it's just any vector here. Okay, but what does it do diagrammatically? Okay, this is exactly why you are drawing the y-axis and the x-axis every time when you draw the R2. Okay, where is 1, 0? So 1, 0 is here. Okay, 1, 0. Should I put it here? Okay, 1, 0. And then 0, 1 is here. 0, 1. Okay. So when you open up this axis here and then this axis here, you can make all the point here. Okay. So that's why every time you draw a R2 graph, you will draw these 2 lines. And then when you draw R3, you will have another extra line. Okay. Make sense? Is it making sense? Okay. Okay. So this is why we care about linear combination. Okay, so for every vector space, okay, we want to find this spanning set. Okay, so that we can break our vectors into a simpler vectors. Okay, so yeah. Yes. Okay, so in this case, right? So in this case, we will say that uh, the set 1, 0 and 0, 1 span R2. Okay, because if we take every vector in R2, okay, we can split them as a linear combination of 1, 0 and 0, 1. Okay, just using scalar multiplication and vector addition. Okay, two operation, scalar multiplication, vector addition. Okay, these two operations only. So we will say that this set span R2. Okay, because R2 is equal to the span of 0, 1, 0. Okay, so this is the, I should write notation for span. Okay, so yeah, span can be a noun, can be a verb. Okay, any question up to now? No? Any question? Be brave to ask. Okay, next. Next, yesterday we stopped at this theorem here. Okay, quite rush. So let's recap this theorem again. So this theorem says that start with a matrix. Okay, the following are equivalents. Okay, if you haven't learned maths before, what does it mean by the followings are equivalent? That means one true sentence true. Okay. One true or true. One false or false. Okay. So one sentence is true, everyone is true. So one is false and everything is false. Okay. So let's analyze what they say, and then we'll see what's going on. Okay, let's prove here. So for A, for every B in the Rm, okay, so you should imagine this B. So for every B in Rm, okay, so we can write B is equal to B1 up to Bm, okay, because there are m numbers there, okay. So this m, so I think I haven't mentioned this notation. So Rm mean you have a real number. So you have m scalar, and then the equation Ax equals to B has a solution. Okay. So let's recap what is Ax equal to B, right? So Ax equal to B. Okay. So what's this? This is what we mentioned in the start. So this is a matrix vector product. Okay. So matrix vector product is what? It's a linear combination. It's a linear combination of the column multiplied by the corresponding scalar. Okay. So you need to split your matrix into column first, column vectors, and then split your vectors into scalar. Okay, make sense? Yeah. So let's see. So so I split my matrix into column. Okay, so how should I write? Okay, let me write like this. So let me split my matrix into column first. And then I split the and then split my x bar into scalar. So x1 up to so the is a linear combination of these two. So is this x1 of a bar n of a n hat. Okay. So this is the matrix vector multiplication, and then we want it to equal to b hat. Okay. B hat is like this. B hat, B hat, B hat. Okay. So too far. Okay, let me move something wrong. So has a solution, meaning you can find the system is consistent, so you can find the answer for x1, x2 to Sn, right? Right? This is a solution. Okay. So if you can find this, so that means the scalar exists. So it is a linear combination. So B is a linear combination of the A1 hat, A2 hat up to AN. Okay. And C, this is just by definition. Okay. Is it anyone confused or not? Anyone confused? Okay. So by definition, B hat is the linear, is a linear, is a linear combination. AN hat if x1 up to xn exists. Okay, this meaning there's a solution. That is the solution equation 1 exists. Any question or not? Any question? No. Okay. Yeah. Okay. So since every vector in Rm is a linear combination of the columns of the matrix, then the column of matrix span Rm. Okay. So what does it mean by the column of A span Rm? Meaning if you take any vector, okay, recall from here. So you take any vectors in R2, you can write it as a linear combination of a vector inside that, right? So it is just by definition again. Okay. So it is really by definition. So one example to keep in mind is this R2. Okay. So R2 is spanned by two vectors, 1, 0 and 0, 1. Okay. And then A has a pivot position in every row. Okay, this one a bit tricky. Okay, so we want to establish D and A. Okay, so we establish D and A, the connection between D and A. So A, B, C are connected just by definition. You just spell out the definition. But D is a bit special. D have to spell out with A is more obvious. Okay, so maybe let's do here again. So A and D. So let's say A and D. Okay, so let's start with D first, right? Okay, so suppose D first. Okay, so if A has a pivot, careful, careful. Okay, if A has a pivot position in every row, okay. So from yesterday example, this one is just an example. Okay. If you have a pivot position in every row, okay, you can imagine that you make it an augmented matrix, ABC. Okay. Then what this says? So this will turns into the solution. Okay, makes sense. So if you have pivot position in every row, then you can solve the linear of system equation. Okay. Is this how you read this augmented matrix? Still remember how to read the augmented matrix? Okay. So in general case, it's the same. Okay. But yesterday we also see that if you have an extra 0 rows, might be consistent, might not be consistent if C is not 0. Yesterday we talked about this. Okay. Okay, so these two will address the connection between A and D. Okay. So the most importantly is you can relate this 4 statement here. Okay. If you want to solve the matrix equation, you need to check whether it's a linear combination of the column of A. Okay. Maybe the question will ask, does the set of vectors span Rm? Okay. Then what you need to do if you need to check this either one of these 3 things. Okay. Okay. Maybe not so much also no use. Maybe I show you examples. Let's try something. Let's try something. Okay. So examples. I think. Check the A first. Check whether A B epic 6 span R. Sorry, too weak. Okay, so this is a multiple choice. I let you think for 2 minutes. Okay, pick A or B, or both, or none. Let's see if you can apply the theorem. So let me move the theorem together so that you can read. See, So if you check one of these is true, then C is true. If you check one of these is false, then C is false. Okay. See which one is better to use. Anyone have tried? Anyone want to try? A or B span R2? Anyone? Anyone want to try A or B span R2? Hmm? Have you tried? Okay, good. So to use this theorem, very good. There's a good point here. This statement is very important. Let A be a matrix. Okay, but any matrix here, I don't give you any matrix, right? So how you build this matrix? Okay, but you should understand it from this line here. Okay, so the columns of A span Rm. Okay, so you have to make these vectors into the column of your matrix. Okay, so you can build two matrix out of these two sets. So one you get 0, 1, 1, 1, and then the other one you get 1, 3, and 2, 6. Okay, so this is the matrix you get. And then you can use D, okay, because we already learned how to row reduce it. Okay, so use B to row reduce it. So if you row reduce this, what do you get? Let's say you make row 1 interchange with row 2, so you get 1, 1, 0, 1. Okay, so in this case, you have one pivot here and then one pivot here. Right. We don't need to we don't need to reach the reduced row echelon form. We just need to check whether there's pivot position or not. It's enough. Okay, because we only care about pivot position. We don't care about reduced row echelon form. How about this? So if you take R2 plus 3R1, you will get 1, 2, and 0, 0. Okay, so there's only one pivot position. Okay, so there's no pivot position in every row. Okay, so this one D is true and C is true. Here E is false, so the two false, hence C is false. Okay. Okay, so yeah, so when you are solving linear system, you also can think of there's a matrix system going on at the background. Okay. Yeah. Any question? Any question to it? Question? Take out another lecture time. Okay, but this one very important. Okay, this one very important. So span linear combination, another skill to calculate. Uh, any question? No. If no, should we break first and then we come back again? let's break. Let's break for 10 minutes. We come back 10:55. Maybe you can wash your face or what.
People position 不应该看。对，那个
想减焦。
对，那个叫做reduce row echelon form。但是我们只是现在我们只想看有没有 pivot position 的。你当然可以把它剪掉，但是我们现在只要看有没有 pivot position。对对。
这个它也是 REF，就昨天上课写的这个。
还没，你还要继续做。
嗯
REF 还没有吗？这个
对
只是 echelon form 吧？对对。
Is everyone back yet? I passed down this attendance sheet. Okay, next we will study the nature of the solution set of the system. Okay, so we care about whether we can solve it or not, or there's a one solution, or there's an infinite many solution. So now we want to study the solution set. Okay. So when we study the solution set, there are two situations. Whether ax equal to 0, okay, 0 vector, and ax equals to b hat, a non-zero vector or 0 vector. Okay. So as everyone knows, this 0 vector here is the vector with 0 at everywhere. Okay. So in this case here, we call it a homogeneous. So we start with understanding solution homogeneous equation. Okay, so you might wonder why Max want to introduce so many words. Okay, so that you don't need to every time say, I want to check ax equals 0, I want to check ax equal to ay equals 0 or by equals 0. Okay, you just say I want to check the homogeneous equation. Okay, one word can include many meanings. Okay, so that's why we want to introduce so many adjectives. Okay, so ax equals 0 always have one solution. What's the solution? Do you know what's the solution? Ax equals 0 always have one solution. You know what's the solution is? Huh? Ax equals 0 always has one solution. Anyone? Any idea? A times the vector, what vectors you will get 0? Huh? 0. Okay, so note that A multiplied with 0, you always get 0. Okay, so to remind you again, so this is the 0 times A1 column, and then 0 times A2. Split your matrix into column. Okay, understand? Okay, so in this chapter at least, so we always like to split our matrix into columns. Okay, so we like to study our matrix like this. Okay, column vectors. So keep the picture in your mind. Column vectors in the matrix. Okay. Hey, so another observation is if you realize from what we calculate before, let us rephrase this way. So the homogeneous equation ax hat equals 0 has a non-trivial solution if and only if the equation has at least one free variable. So because A, when you reduce to row echelon form, right? Okay. So what do you get? For example, let's take an example. The 3 times 3 case. Okay, we have the 7 type, right? So if you have 1 0 0 0 1 0 0 0 1, okay. If you have this row echelon form, you augmented with a 0 vector here. Okay. So this is coming from here, if you wonder. Then this means what? X1, S2, S3 have to be equal to 0, right? Remember how to get this solution out? So x1 plus 0 times x2 plus 0 plus s3 equals 0. And then I just write the result. Okay? For augmented matrix, you go to linear system equation. Okay? So you only get one solution. Okay? But if it is, for example, yesterday we have this case here, 0 on the row, then you can get non-trivial result. Okay? So let's give an example like this. Yeah. So this means what? Remember how to read the solution? X1 equals to 2. Yeah. Should I use this? Okay, just use this. S2 equals to 3. S3 is 3. Not 3, 3. Right? 3. So what 3 means? So this solution can be 2, 3, 1, 2, 3, 0, 2, 3, anything. Okay, 6. All are the solution. Okay, so there's infinitely many solutions. Okay, so if you have one variable, it forms a line. Two variable, it forms a plane. And then this line and planes will pass through the origin because origin is always a solution. Okay, so yeah. So at least one free variables, you can have infinitely many because it's free. So you can choose any number you want in that variable. Should we? Okay, let's test you again. See if you can do row reduction. Okay, let's do tutorial first. Okay, let's do this. Try and row reduce this. Okay, row reduce this homogeneous system. Okay, another way of asking the same question, but it asks whether the following homogeneous system has a non-trivial solution. Okay, try and row reduce this. Then we will check answer together. Don't care about this parametric vector form first. Later we will talk about it later. And try reduce this system of linear equation. So there are a lot of ways asking the same question, but using the same way to solve. Is it too small now? You make it bigger. 1 more minutes. Anyone done the calculation? Any free variables? Free variables? Not yet. Huh? S3? Okay, let's see. So you get S3 is free. So how to solve this? So you got a system of linear equation. So equivalently, you can get the augmented matrix. Right. So augmented matrix is your coefficient matrix plus the constant vector 0, 0, 0. Okay. So how to row reduce? Okay. Let's see what I do and then you compare what you do. Which one better? Okay, what I do is I add the second row to the first row so that I get 0, 3, 0. Okay. And then keep the row first. And then what I do next is I take R3 minus 2R1. Okay. So what I get 0. And then I get minus 9. I get 0 again. Okay. So you can see from here pretty clear already. These two are scalar multiple of each other, so we can cancel it. So what I do next is just R3 plus 3R2. Okay, so I insert the last row, so I get 0. Okay, and then shall I continue? Okay, let's continue. So just 2 more steps. So I rescale the second row, and I get 0, 1, 0, 0. So I get my pivot already. Okay, I still need to make 0 above the pivot column, pivot position, I mean. So I need to take row 1 minus 5 row 2. So then I make a 0 above the pivot position. Okay. What's the last step I do? I need to make the first leading entry to be the pivot position. So I need to scale. And I get the reduced row echelon form. Reduced row echelon form. Yeah. Okay. And is everyone getting this reduced row echelon form? Is it the same one you get? Check your solution. Okay. So from here, okay, this one is very crucial. From here, how to translate to general equation? Okay. So I already skipped step. So I will get x1 minus 4 over 3, x3 equals 0, and then x2 equals 0. Okay. So what's the general solution? What's the parametric description? So is x1 equals to 4 over 3 x3, x2 equal to 0, and then s3 is free because there is no condition on s3. Okay, but this question asks for parametric vector form. Okay, so how to turn this guy into a vector? Okay, so how we turn this into a vector, right? So the vector they are looking for is x hat. Okay, x hat made up of x1, x2, and x3 in this case. Okay, so from here you can see x1 is what? What is s1? 4/3 x3. Okay, what is s2? 0. S3 is 3. So what does it mean by S3 is 3? So S3 can be anything. So S3 again. Okay. So from here, you can do the scalar multiplication to make it nicer. So this is the vector you want. 4/3, 0, 1 times x3. Okay. So this is the parametric vector form. Is it clear? Make sense? Make sense? Any question? Any question? No? Okay. So if the question asks for parametric vectors form, then you need to transform this into this vector form. So next, okay, let's continue. Let's leave this out. Okay, can we do this? So question. So we have already looked at the type not homogeneous. How about solution of non-homogeneous system? Okay. So let's say the B is not zero vector anymore. Okay. So what to do? Okay. One simple way is to just do the same row reduction method. Okay. You have the same matrix, but you have a different. Okay. Let's say I change the question just now. Okay. Let's change to, for example, 7, -1, and 4. Okay. So what when I change these, right? So you imagine that there's a 3 variable here. So they define a plane. So the plane tilts differently. Okay. When I change this variable, the plane tilt. Okay. So when they tilt, you should imagine the solution might change. Okay. So how it changed? I don't know. Let's see. Okay. So we do the same. If we do the same row reduction, okay, and maybe we don't, for the sake of time, we don't repeat it again. Let's see how the constant change. Okay. Let's do the same row reduction. Okay. So if you do the row reduction, the coefficient matrix part, the row reduced echelon form is the same. Okay. So how does the constant change? If you go through the process, you get -1, 2, and 0. Okay. Is the system consistent? Is the system consistent or not in this case? Yes or no? Huh? Yes? Why? Why? Huh? Is the system consistent? Yes or no? Yes, sir. Because this the row of 0 here, there's no constant, there's no non-zero constant here. Okay, so this system is consistent. Okay, and there's a free variable, so that means you have infinitely many solutions. Okay, so how do you write down the parametric vectors form in this case here? So what you get is let's do it again. X1 -4/3 x3 equal to -1, x2 equals to 2, x3 is 3. Okay, So in parametric vector form, what do you get? X bar is equal to x1, x2, x3. And then x1 is minus, okay, let me move it down. Okay, so x1 is equal to -1 plus 4 over 3 x3. S2 is 2, S3 is 3, so it is itself. Okay, and then what can we do? We can split into vectors form. So we will split into a constant part and the part with a variable. Can you see this two is the same? Okay, so if you add these two up, you get this part. If you add these two up, you get the 2. And then you add 0 and S3, you get S3. Okay. And then the reason I want to do this because I want to take out the S3. Okay, so I combine the S3 term together. So what I get is -1, 2, 0 plus x3 4 over 3, 0, x 1. That's okay. So you should realize that this is the solution we get for homogeneous equation just now, right? Okay. Right. See? Okay. So this is the homogeneous equation plus an extra bit plus a constant bit. Okay. So actually, so what I'm saying here is this theorem. So let me give me bigger. So if you have a solution of ax b hat, okay, you call it a P, then the solution set of the ax equal to b is the set of all vectors of the form P plus the solution for the homogeneous equation. Okay, so it's the whole line shifted by a constant. It's the solution for ax equal to b. Okay, so that's why the solution of homogeneous system is important. Okay, because all those equations that provide a different solution to the same system, to the same non-homogeneous system. Okay, make sense? Okay. All right. Okay. Following, following, following. No, following. Any question? Okay. So it's a non-homogeneous solution plus a constant. Okay. To spell it out, okay, maybe I spell it again. So let me how do I expand? Okay, expand a bit. So suppose ax equal to b hat and ay equal to 0 hat, then ax hat plus ay hat is equal to b hat. Okay, because ax hat plus y hat equals ax bar plus ay bar, which is by 0 bar. Yes. Okay, so you can add all the non-homogeneous solution to your non-homogeneous solution to get a new solution for the non-homogeneous system. So in this case, so the option is in this case, you produce new solution to the equation. Okay, so it produce new solution. Okay, to not confuse you, maybe I use W here. So you produce new solution. You don't not just have W, you have W plus Y. Okay, and Y have infinitely many, so you produce infinitely many solution. Okay. Okay. What's the time? 9:19. Okay, let's go into linear independence. Okay, so this part, most important part is the translation and then the parametric vector form. Okay, the next part, we will talk about linear independence. Okay, so you will see, you will keep seeing that linear combination, linear independence, we will keep using the word linear, okay, because there's no square involving here. Okay, so we will say linear. After all, this course is called a linear algebra. Okay. So everything is linear here. Okay, so what's the linear independence? Do I have the, yep, I have the solid definition with me. So what's a linear independence? So this has to be a relation between vectors, okay? Because we care about vectors now. So what's this relation here? Relation on vectors. How are they independent with each other? Okay. So what do you mean by independent with each other? So they are called linearly independent if you consider the linear combination of the vectors such that they're equal to the zero vectors, the only solution is the trivial solution. Okay. Okay, so this is the trivial solution. So I think the first time I saw this definition, I was also confused what's going on. Okay, so let's look at two variables. Okay, let's look at two variables first. Let's look at two variables. What's going on? So for example, let's say we only have V and W in our case. Or anything. Okay, so two variables. So you need to set up the vector equation first. So plus, okay, I should put a arrow because this is a vector. So let me set out this. Okay. So when are they equal? When this vector equation equals 0? Okay. When this equation equals 0? Any idea? When this equation equals 0? When this equation equals 0, such that it has a non-trivial solution. Can you play around with this equation here? So maybe I move W to the other side. Okay. And then I try to move X1 across as well. Okay. So this says that, okay, if V hat is a scalar multiple of W hat, W, then there exists a non-trivial solution here. Okay. So maybe doesn't make sense to use it. Okay, so let's look at two. So linear independence. Okay. So in this case here, okay, so for example, should I use this card? So this one, white, and then I can use another blue one. So this one is the B, this one W, this one V. Okay, so V and W are linearly dependent. Because it's a scalar multiple of each other. Because, okay, linearly dependent meaning I can get W from the others, from V. Okay. Yeah, linearly dependent means I can get W from V. Okay. So if you can see that if what do I say? Okay. So okay, maybe I give you an example, another example, linearly independent example. Okay, ask another question. So why we draw y and x? Okay. So not only every vector can written by these two vectors, they are the span, they are also linearly independent. Okay. What does it mean? That means if two linearly independent vectors put together, I cannot obtain one from each other. Okay. That means I cannot, let me write it out. So 1, 0 and 0, 1 linearly independent, because I cannot obtain one from another. Okay, so no matter obtain meaning what? You can only do two things: vector addition and scalar multiplication. You cannot multiply one number on 1, 0 to get 0, 1. Okay, you can never do that. Okay, so this is the linear independent means for two vectors case. For more vectors, you can use only two operation. Only two operation you can use: scalar multiple and vector addition. Okay, these two. Okay, so if a set, okay, so let's say another observation here. This one, maybe first. Okay, next, let me say another condition. So if, okay, the key is here. If V, if a set Vn is linearly linearly in is linearly dependent, okay, then I can write, okay, let me, instead of putting so many things here, let me just do 3 variables, because this one can extend to all the cases. If this 3 set, this one is just fact. If you have 3 vectors that are linearly dependent, then I can write V hat in terms view, and okay, not in terms, in the linear equation W hat and Z hat. Okay, so if it is, if, okay, if V hat, W hat, and Z hat is linearly independent, then I cannot rewrite right, any vector in the linear combination of so I think okay, the first case here I can rewrite, I should say I can rewrite one vector in terms. Okay, so okay, a bit, is it confused or not? Bit vague, a bit vague. Okay, maybe just try example again. Let's try example. Let's check for the set. I'll show you example, right? Okay. Show that 0, 1 and 1, 0 independent. So show that these two are linearly independent. So let's check for definition. Okay. So what's the definition of linearly independent? So consider the vector equation. So C1 times 0, 1 plus C2 times 0 equal to 0, 0. So the question is, does this have a trivial solution? Okay. If yes, then they are. Because you cannot view another vectors from scalar multiplication or vector addition. If, sorry, did I do something wrong? Okay, this one is linearly, if yes, okay, if yes, sorry, if yes, they are linearly dependent. If no, then they are linearly independent. Okay, so let's see. Any question or not? I think I say a lot of thing not organized together. Okay. Yeah. Okay. So okay. So you got a vector equation. So what do you do? Can you get a momentum matrix like this? Okay. And then you can row reduce it to 1, 0, 0, 1. Okay. Which tells you that C1 is 0 and then C2 is 0. Okay. So this is a trivial solution. So trivial solution will lie in the case of 2. Okay. So this is a case. So 0, 1 and 1, 0 are linearly independent. means, okay, let's look at what does this solution means, okay? So this means that 0 times 1, 0 plus 0 times 0, 1 is equal to 0. Okay, so what does this mean? Okay, maybe we do something crazy. So we move the 0 at a minus here. Okay, so this means that there's no relation between them. Okay, the only relation you can put between them is 0. Okay, that's why the condition here. A set of vectors is said to be linearly independent if the vector equation, when you set the linear combination of the vectors to 0, it only has a trivial solution. Okay, because no matter how you arrange the equation, there's no non-trivial relation between them. Okay, the only relation you put is 0. Is it better now? Is it better now? Okay. So for example, let's give you an, maybe you don't believe something is happening here. So give you another example. So next example. So a 2, 3 is, okay, maybe I put 6, 4 is linearly dependent to 3, 2. Okay. So the claim is 6, 4 is linearly dependent to 3, 2. So that means, again, that means there is a non-trivial to C1 times 6, 4 plus C2 times equal to 0. So can you guess what is C1 and C2? You don't need to do row reduction. Can you guess what is C1 and C2? 1 and the -2. 1 and the negative. So you can pick C1 equals 1, C2 equals to -2. Non-trivial solution. Let's play around with this equation again. Again, what does this mean? So this means that 1 times 6, 4 minus 2 times 3, 2 is equal to 0, 0. Okay. And then 6, 4 is equal to 2 times 3, 2. So there's a relation, non-trivial relation here. Okay. You can write one vector in terms of other vectors. Okay. So that's why the equation set to equal to 0. Okay. So the relation is just a scalar multiple and a vector addition between the vectors. Okay. That's why we set this vector equation equal to 0 here. Okay. Because we only want scalar multiple and a vector addition between the vectors we can. Okay. That's why we put 0 here. Okay. 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 There's some theorem here. First theorem is if you have p vectors, okay. So when are they linearly dependent? As long as one of them you can write as a linear combination of the others, that's enough. Okay. No need all of them. At least one of them is enough. Okay. One vectors from the set that can be written as a linear combination of the others is enough to say that the set is linearly dependent. Okay, one is enough. Okay, you can see from this diagram here, if W lie in the is a linear combination of U and V. They will lie on the same plane. Okay. And then if it is linearly independent from the two vectors, then it lie outside the plane. Okay. So this is the geometry part of a linearly dependent and linearly independent. Okay. And then the next thing is if you living in Rn, okay, and you have more vectors than the number n, then the set of vectors must be linearly dependent. Okay. So maybe let me give you an example of R2. Okay. So the claim is if you pick any three vectors here, okay. For example, 0, 1, 0, 2, 2. This set is always gonna be linearly dependent. This is a bit like the pigeonhole principle, okay? Because you have more things inside, so you must use the other two to make up the one, okay? So the claim using this theorem, this set is linearly dependent, okay? So why is it linearly dependent? Any idea? So from the previous example theorem, you only need at least one that can be written as a linear combination of the others, then this set is linearly dependent. Okay, so which one is linearly can be written as a linear combination of the other two? Which vectors can be written as the linear combination of the other two? Any idea? Okay, let's should we recall or should we? Okay, the question is, can you write can or not? Huh? Any ideas? Any idea? Can you write one vectors in the set as the linear combination of the others? Any idea? You write one vectors. One. Simple. You want to say anything? Huh? Say again. Uh-huh. You mean okay? So 2 2 is equal to 2 times 1 0 plus 2 times 0 1. Right. Okay. So you found a linear dependence equation between the between the three vectors. So this is the so this is so as you say 1 minus 2 minus 2 is a solution to C1 2 plus C2 1 0 plus C3 0 1 equals to okay. So these two formulations is it easy to see or not? So what I want to say is the upshot is this two is expressed same idea. Okay. So to solve the vector equation, okay, it's the same as asking whether a vector is a linear combination of the others. Any question? I think a lot of you blur already. Any question? Any question? Any question before we proceed? Yeah, independence. Should I give you some more ideas? Yeah, maybe you ask me some question. Any question? Class until 11 o'clock, right? 1 more hour. So maybe let's see. Let's get one question before we break. Okay, get one question from this class before we break. I think I messed up just now, so try ask me one question. Any question? If you want me to repeat the definition of linear independence, I can try again. Any question? Okay, one question before we break for the last hour. Just one question from the lecture. Anyone? Quick. Only one question. Question from any one of you? If not, then I call name. Where's the attendance? Call new student that I don't know. It's Marvis Smoke. Marvis Smoke. Do you have any question? So far, no? If no, can you explain? You mean what is linearly independent to you? To you, I mean, yeah. Can you explain? Just in simple word, what does linear independence means to you? Right? If you cannot explain, then you must have question. So either one. Don't understand.
Need time to revision myself.
So I mean, at least for now, what do you have? What's your impression on linearly independent? What's your name? What's your name? Yeah, the middle one. What's the name? Elvin? Huh? Which account? Okay, account. What number? Last three number. 006. Oh, Gao Lu. Okay. So what's linearly independence means to you? Say again. Oh, you mean the vectors equation set to 0 only has trivial solution? Linearly independent. Okay, good. Okay, this is the definition. So if you want to say in that set, a set of vectors are linearly independent, the only solution to the vector solution, a vector equation set to 0 has the trivial solution. Okay, this is the definition. Still not satisfied yet. Let's call another one. Someone from finance. I want to see if how's finance given. Sentoso. Is Sentoso here? Sentoso, yeah. Okay. So what's the linearly independence mean to you? What does linearly independence mean to you? If you cannot answer, you can ask me one question. I think it's quicker. Or maybe you know the answer, you can tell me. Oh, not enough. Okay, not enough. Not just the linear combination of vectors equal to 0 vectors. You need to make sure you have only the trivial solution. Okay, only trivial solution. You get what I mean? Okay, when you set it equal to 0, it just says that you want a relation between them. But what kind of relation you want? Okay, is it a trivial relation or a non-trivial relation? Okay. If it is a trivial relation, then there's no relation between the vectors. If you have a non-trivial relation, you have some non-scalar solution to solve it. That means there are. Okay. Okay, one last person, one last person. Zhang Shuai here, no? Zhang Shuai. Where's Zhang Shuai? Zhang Shuai? Okay. Do you have a question for me, or you want to explain what is linearly independent? You have a? do you want to ask me a question or you want to answer what is linearly independent mean? Pick one. Hmm? Yeah. Pick one. Before we break. So one, ask me a question, or two, answer what is a linearly independent means. Quick, 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 quick. Hmm? Before we break. Come. So what does linear independent means? Just look at me. Hmm? Or you can ask me a question, any question. Any question. Ah, I still remember last time Wen Zhaoling asked me why we study this. Question? Before I break? No question. No question. You have to tell me what's the linear independence mean. No question. I don't force you. So, let's come back at 10:07, and then we'll talk about linear transformation. Okay, let's have a break. If you in the break, you think of any question, then later we'll address again. Okay, 10:07, we come back.
À,来，对对，很慢，做比较快。你看，为什么会很慢呢？哦，我知道你为什么很慢了，因为你是不是一个一个把它变成一啊？我是不用紧啊，我是来，你先把 pivot 那个 leading entry 找出来，然后你到最后的时候才把它变成一，对吧？比如说你已经知道你想把它变成一了，你先不让它变一先，你可以先做其他先。 啊，你不用每一步都一找到我就把它变异，一找到我就把它变异。有时候不用变异也可以算得到，也可以不是讲算得到，就每一个都算得到，但是就不用花这么多步。
就是有一个问题，
也
前面有个 equivalent 是
啊，上，去开始的时候，开始的时候，一开始的时候，
对，
这个
对，看一下，就是，嗯对，就
，OK，
是对，他说有个pivot
对
position in every row，
对
然后就是像这个 matrix 里面，就是这一行就没有一个，
对，没有
嗯，
错。
然后呢，它的 solution 是这个，
它不能啊，因为你看啊，它这个最后的零等于，就这有一个 contradiction，这个
那
也
这个改成，
改成零，OK，改成零，OK，改成零可以
然后这个算是一个 solution，
，yes，
然后那就是对应
yes，
A 这句话，
啊，对，没有错，
它
它有很多首选，但是它有一个错，对，
嗯。
对，
就是说，那这样的话就满足了 A，是吗？
哦，我知道了，因为你看啊，A 这个啊，记得我们学 discriminant 的时候，这个是讲 for every B 嘛，你这个只是一个 B 吧？你看，如果我换去5就没有了哦，是不是？啊，对，所以呀，对呀，OK 吧？嗯，好，
就我们看看
对
这个例子里面，这个例
对
子里面，
，OK，
相当于这个里面的这个，
VH 对，
然后我这个，那我现在不是说我这个，
嗯，
呃，A AX 等于 B，那我这个，那我这个，它不是说 X等于 B 吗？那在我这个里面，P 是一个什么？
哦，
它现在后面又变成 X 等于 B，
对，所以你看这个 part 就解了这个部分嘛，然后这一个 part 就解这个 AX 等于 B 的部分了。为什么你这个只有 ABC 吗？
就我是假设，就假设
哦，
我是或者，因为它可能是直接可以表示或者后面要加一个东西，
等一下啊，我看一下啊，
因为现在是从零开始嘛，
对，
因为现在从零开始，
对，
如果从零
这个，
开始，
嗯，
就挣出来了，呃，
这一个不是给
P 的话，
嗯
它前面这个但是你看这个成立的理论是，但这个是零，然后放成这个条，
对，
像这种的话，应该是后面不是零，就后面有数字。
你有记到我有另外一个 example 吗？
有，这个我没记，但是
哦，你没记？
对，
对，对你现在要表达什么到底？
就是你看但它这个理论是从 ax 等于零推出来的，可是 ax 等于零，它后面没有这一项，
对
x 等于 v 加 p，它是只有 x 等于
对，
一项。
这个 P 它是说，你看 the equation of 这个 has a solution given by the，意思说它已经解了这个东西，听明白吗？
就是这个 p 的话，它也可以是这种形式的，对吧？两项之后，
可以两项之和，也可以这一个罢了。比如说，你看我这个，你看我这个啊，看我这个，我刚才不是有说我把那个题目改掉，说把那个
小数字，
对，然后你看啊，我的这一个东西啊，这里 是变数
在上面。
上面，给这里，你看啊，你看这里，你看，就算我不看这一个啊，我不看这个，把这个当做你的 P，你去解它，你也可以拿到那个的，所以
可以啊。
啊，S3可以是零啊，可以是任何东西，所以你这个拿来乘一下，你看一下是不是那个7减1跟4减4，
嗯，
所以意思说这一个是一个解，给它是个解，
这个
可以吗？
这个
嗯
theorem 就是说，
嗯哼
如果这个它已经有解的
嗯
话，
对，然后你只要把这个解加上你之前那个等于零的解，都是它的解。
我就是如果
Yeah
它有解的话，
对，它有一个解
它，有一个
然后你
解，
加上之前呢，它整个都是它的解。嗯，
哦，它之前的像是通过这个算出来的。
没有错，
哦，
没有错。
所以说
对，你看他每次说意思的时候就算这个，意思说他已经算出来了。他怎么算不知道，他已经算出来了。
就这个的 theorem 就是说，如果我有一个
对
已经有已
Yes
知的解，
Yes，
然后我想找到它所有的解，我就可以让 x 等于零，然后去这样找。
没有讲是，给我看一下。OK，可以，OK，可以，对，所以这个解加上所有能够解掉这个 homogeneous 的 equation 的解，
就是它的所有解。
对，
还有这个，就他上课讲的这个图，画了一个这个图，
嗯
就是他这边是负号的话，它这个 direction 又变成
depend 哦，这个 depend on 这个 S2 S1 哦，如果里面有解的话，再也可以消掉，depend，这个只是一个情况，所以意思说，如果这样子反着的话，也算是
算是
linearly 嗯，如果 b 不等于零的话，零乘 x1，零乘 x2，零乘 x3等于一个不零的东西，不可能。所以，如果你要找，如果这个 system 是 consistent 的话，就是说你不可以有 contradiction 的东西哦，你不可以有那种怪怪的 equation 在里面，有不对的 equation 在里面。
所以它应该是
有，诶，对，存在 if b 等于零，if 这个 part 等于这个 part 不等于零就存在。其实
但是它不能等于
它，我在写什么？哦，没有，这个是我不知道它等不等于零，但是它有可能等于零，它也有可能不等于零。我是想说，如果它不等于零，那就没有答案，就 inconsistent。如果它等于零，它就 consistent。两个可能性，depend on 这个 B3、B1、B2。
这个的话，它要满足什么条件？就是去过它要满足全部满足是
你是说
dependent
for dependent 啊？dependent 是呀，对，不是，只要一个就够了，不用所有，懂什么意思？可以有些是零，但是不一定是所有东西，可以有些零，有些不是零。嗯哼，
要有
只有零的解，零肯定是一个解，但是只有零的解。
加减
加减没有，就没有关系哦，因为你只有零可以放进去嘛。
x 是
再讲一次
x 是 v 是零的，
啊？
现在是 x 是零的，
对对对对对对，
只有 x 对零的时候，
independent 的话要每一个都是零，S1 S2到所有。一个不为零，它就是 dependent，对，一个不为零就啊，对，啊对，没错，没错，嗯，
就
那个啊哈，
嗯
对，x 等于 b 有一个解，then 所有的解你可以用 p 加这个 bh 是 ax 等于零的解，这两个加起来就是所有的解，你 get 到？对，p 可以解掉这个，vh 可以解掉这个，但是所有可以解 ax 等于 b 的解是它们的和。
这样子。
addition，OK OK，
Hello. Okay. Okay. I think I got some good question from you. Okay. First one is this one. Okay. So how to understand this theorem here? Okay. So this start with there's two part here. Okay. If this, then this. Okay. So what is this theorem saying about? So if you have a solution for AS equal to B, okay, that means call it P, that's in AP equals to B bar, okay. And then you also have solution to AS equal to 0, AVH equals 0, okay. Then the claim is, okay, I know that AP is B, okay, I know this because from the condition. Then the theorem is, if you add P with VH together, okay, it still solve the equation. Okay, so this, and in fact, this is all the solution. Okay. So you have a solution for AS equal to B, and then you add all the solution to the homogeneous system, and then you will get all the solution. Make sense? Make sense or not? Make sense? Any question? Okay. Yeah. Okay, the next bit is the definition of linear independence. Okay, so let us do one summary here. Okay, let's do summary here. So when I talk about linearly independence, remember this is a relation between vectors. Okay, so how you play around vectors, play with vectors. Okay, you only can do scalar multiplication or addition. Okay, let's look at the equation, vector equation C1 V1 hat plus C2 V2 hat plus Cn Vn hat equals 0 vector. Okay, let's look at this vector here. Okay, let's look at this vector between vectors V1 hat. We look at this vectors here. So we ask ourselves, because this is a vector equation, right? It is also a linear system. So we can ask whether this is what? This is, does this has a trivial solution or two cases? plus what is it? Trivial solution, or non-trivial solution. Okay. So trivial solution means, okay, maybe I didn't explain just now, means C1 up to Cn is all 0. Okay. Non-trivial means at least one di is non-zero. Okay. So if it is trivial, then there's no relation between them. Okay. So no relation between vectors. Hence, they are linearly independent. So if there's non-trivial solution, then there is a relation between vectors. Hence, they are linearly dependent. So linearly independent, you set up this vector equation, okay, and then ask yourself, do you have a trivial or non-trivial solution? Okay. This is the definition. Okay. Any question or not? Yeah. If you want to ask me why we care about this equation, it's because this is the only thing we can do with vectors. You can only scalar multiply and vector addition. Okay, this is all we care about vectors, linear combination. Okay, and then the most important thing is set to 0. Okay, and then solve it. If trivial solution, no relation, linearly independent. Non-trivial relation, at least one of them is non-zero. There's a relation, hence they are linearly dependent. Okay. Yeah. Okay. Next. We already know how to check something is linearly dependent and independent. Okay, next we will do linear transformation. This one is a bit closer to what I did in the research. So, have you all learned about function? So function is you input, I give you an input, function will give you an output. Okay, and this transformation is a kind of function, but it's a special kind of function that go between Rn and Rm. Okay, this is what we call transformation. And then later we'll see that what it transforms actually. Okay. So it's a function, okay? I give you a vector in the domain. Okay, this part is the domain. Then the transformation will give me something in the codomain. And then the thing that T maps to is called range. Okay? Range is where T hits. Okay. Let me see. Okay, I think there's a good example. So, example y equal to x. Okay, is the transformation. Okay, let me make a black box out of a black box and then try to do something crazy. So let's look at y equal to x. Okay, this is the function. Okay, when we read this as a function, usually we write fx equal to x. Okay, I give you an x, you give me an x. Okay, and then this f is going from R to R. Okay, you give me a number, I give you back a number. Okay, you give me 1, I give you back 1. You give me 2, I give you back 2. Okay, so what happens? Okay, so what happens is this is a number line. Okay, 0, 1, 2, 3, 4, 5, 6, then -1, -2, and then so on. Okay, and then what you do is actually you tilted the line like this. Okay, so you could imagine that you move this line to this line. You transform a real number line to another real number line. Okay, that's why we call it a transformation. Can everyone see it? Everyone see it? You give me a number line, I produce another number line for you. Okay, so you go like this to like this. So you transform the real number line. So when we plot these two together, you can see that there are two number lines here. Okay, make sense? Make sense? Can you imagine or not? Any response? Okay, so this is one of the transformation, simple one. So you can see that the blue part is the range of f. Then this so this is the codomain. So this is the domain part, and then the whole thing here, is the codomain. Okay, so you can see that the range of f is usually lies inside the codomain. Okay. Any question? Any question? Any question? Okay. So these are the domain, codomain range. Okay. Okay, and then what next? Okay, so let's see. So let's look at some examples of transformation here. So for example, we got this matrix here. Okay. We got this matrix here, and then we got some vectors. Okay. So the question is, we define a transformation from R2 to R3. Okay. So meaning we put something in R2 into the space of R3. Okay. You can put it like this. You also can put it like this. Maybe you can put it like this. Yeah, there's different way to map it. Now let's see what happens to this matrix here. So the definition is, you give me a vector, I take a matrix, multiply the vectors. Okay, okay, let's try and find what is TU bar. Okay, try and find what is TU bar. Okay, so TU bar by definition is AU. Okay, what is A? A is -1335 -7 times 2 minus 1. Okay, so what do you get? What do you get? What's the matrix vector multiplication here? What matrix vector product? Remember, this is a linear combination of this one and the column and the scalar with the column. Okay, so it's 2 times 1, 3. Minus 3, 5, 7. What do you get? Wait, sorry. Right. Minus 3, 5, 7. Do you get? Okay. 1 and minus 8. Okay. So you send, right? What? Minus 9. Okay. Luckily, you awake. Okay. So, so you send this vector to another vector in R3. Okay. So this is only you do on one vector. Okay. So find and next question is find an x in R2 whose image under T is B. Okay. So let's write down what it means. So find an x in R2 such that find x such that x tx bar equals to b bar. Okay, so image under B under T means T apply. Okay, image under T means T apply to X is B. Okay, image. Okay, so how to find? So T is what? Tx is Ax equals to B. Okay, X equal to B again. So what is this? This is the, you need to do the augmented matrix again. Okay, so what's B? B is given, so B is 3, 2, minus 5. Okay, so can you find an X? Meaning you can find the solution or not? Can you find the solution? So is the system consistent or inconsistent? Right? Okay, same question. Okay, different way of asking. So how do you reduce this? Maybe you can put R3 plus R1. What do you get? 0, 4, and minus 2. Okay. How about row 3, row 2? Row 2 minus row 1 is what? 0. 5 plus 9 is 14. 5 plus 9, yeah. And then 2 minus 9 is minus 7. Okay, 0, 4. Then make sure I'm correct or not. Scared I'm wrong. Which one is better? Okay, maybe I scale the second one better. So let's scale it. Row 2. Scale the row 2. So I get 2n minus 1. Okay. Wow, now it's clearer. Okay. So what do I mean by clearer? You can take row 3 minus 2 row 2. Okay. So you can see that you have two pivot. You have two pivot here. Okay. So what you can do, you can write x1 minus 3x2 equals to 3, and then 2x2 equals to minus 1, which means x2 equals to x half. Okay. Okay. maybe this one, keep it first. Very not clean. So let us clean it. So let's clean it here. So what we do is we scale the pivot position first, so that we get a pivot position. And then we clean out the position pivot column. So R1 equals R1. So what's this? 3 minus 3 over 2. What do you get? 6. 3 over 2 again. 3 over 1. Correct? Correct. Okay. So this means I get x1 equals to 3 over 2, x2 equal to. Okay. So this is the x bar equals to 3 over 2 and minus half. Okay. 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 Next part is there more than one such x? Okay. Is there more than one such x? So it is. So no. Is there more than one such x? Okay. Be careful. Is there more than one such x? I think by the theorem just now, yes, right? Because you can add the homogeneous system, the solution to the homogeneous equation. Okay. So the next part is no, there is let me see. There is more than one such, because by theorem we can add the solution of the homogeneous system to x bar to form a new solution to ax bar. Okay. So if you don't believe, right, try go and solve. Go and solve ax bar equal to 0 bar. Okay. And solve denote the solution by w bar. Okay. Then w bar plus the s we have just now is a solution of okay. So you can try and do this because we already tried just now. So if you can try again, convince yourself. Okay. This part is determine whether C is in the range of T. Okay. So you want to ask whether it's the same question as B actually. So determine whether T can hit C or not. Okay. So the third question is determine whether C can be hit by A. Okay. So here I let you try. So whether C can be hit by T or not. So let's copy the question and then let you try. What's the solution? Maybe I just do it here. So C. Determine whether C is in the range P. So meaning does there exist an X such that Tx equal to C? Okay, so I need to solve this. Try solve this augmented matrix. Okay, try solve this augmented matrix. Can you find an X such that Tx equal to C? So the row reduction should be the same, just that what happened to the constant is different, right? Because you have different constant here. So let me see what's the row reduction we get. Okay, so we can row reduce to this form. Okay, so can anyone get what's the constant? The back. Just let me know if anyone calculate out what's the constant at the back. What's this 3 constant become? Anyone got 3 constant? Anyone get it? Anyone got it? Ling, you got it? What do you have? 3. Say again. 3/2. Okay. How about second one? 1/2. Negative. Okay. N. Okay. Does anyone else got the same constant? Anyone got the same constant? I didn't calculate, so see if you get the same one. What you get? You get the same? Get the same? Okay, good. Okay, good. Okay, I think this one should be the right answer. So you can see that this system is consistent or inconsistent? Huh? Consistent or inconsistent? Inconsistent, right? Why? Because 0 is not equal to 10. Okay, so you cannot solve the linear system. You cannot solve the linear system, you cannot find the x. Okay, so there's no x such that tx equal to c. So same method, different way to interpret it. Okay, different way to interpret it. But in this linear transformation, you need to know about what is the domain. You need to know about the word domain. Domain, codomain, image, and image. Okay. So domain is the input of transformation or function in general, and then codomain is the space where the output of the transformation is the output of transformation. And then range is the set of all image. Okay. So range is consider all the image, and then image is just an output of the transformation. Okay. Domain is the input of the transformation. So your transformation need to be able to tell me everything where the domain sent. Okay. Okay. Yeah. Are you guys understanding this example? Yes. Yes. Okay. Because I can give you another. I give you another example, and then we will contrast these two. Another transformation is this one. Okay. How does transform the real line? How does transform the real line? X squared. Any idea? I think you sketched it in high school before. Okay. It bends the real line. Okay. So it makes the real line like this. Okay. This is what you always draw on this. Okay. So you bend the line. Okay. Yeah. But these two, right? These two transformations are different. Why? One is linear, one is non-linear. In this class, we only care about linear transformation. So what is linear transformation? So linear transformation is easy. Okay. Only satisfy these two properties. Why two? Remember what two operation we can do on vectors. One is vector addition. Second is scalar multiplication. So we want the transformation to preserve these two properties. Okay. So what do I mean by that? So if you have two vectors, okay, you can send the vector across using linear transformation first. Okay. Oh. Okay. So you can send two linear transformation first, and then you add them together. Right. Okay. The other way is you can add them together first, and then you send across. And we want them to agree. Okay, that's why we got the first condition here. Second condition is also the same. Okay, you got a number. Okay, let me put and to differentiate scalar and vectors. And you, okay, you can first do. You can first send u across first. Okay, and then you can multiply them, or you can scale your vector first, and then you send across. Okay, and then we want them to be equal. So we want the transformation to respect these two operations. That's why we have this condition here. Okay, these two conditions here. Anything that satisfies these two conditions is a linear transformation. And then you might ask, why we care about linear transformation? It's because matrix transformation are linear transformation. So linear transformation between, okay, I use some jargon first. So linear transformation between finite dimensional vector space, meaning you can put Rn, Rm, okay? You can realize them as a matrix. Can be realized as a matrix, vector multiplication. Okay, so finite dimensional. So when this one is finite, okay, so sum n and sum m. If it is infinite, then the matrix will be very big. Maybe not easy to describe, but when this is finite, we can write them as a matrix. Okay, so all the linear transformation between Rn and Rm is a matrix transformation. Okay, we can use matrix to study them. Okay, so this is why we care about linear transformation. And then some properties of linear transformation. You must send t, you must send 0 vector to 0 vector. Okay, you can see, okay, yeah, okay. So this is an easy easy consequence. Okay, so okay, let's do it. Okay, so why is send 0 to 0? So we know that v hat minus v hat is a 0 vector. Okay, then we can apply t to both sides. Okay, let me do like this. Okay, so we can apply t to both sides because they are the same vectors. Okay. By linearity, we can split them up. By the definition of a linear transformation, we can split them up, right? So remember that you can split the sum and you can pull out the scalar. Okay. Okay. Split the sum and then pull out the scalar. Okay. So now we split the sum first. Here. So we can pull out the scalar. Okay. So TV and TV is equal. So this is 0. Okay. So it sends 0 to 0. Okay. And then B, you can see that you can split the sum, okay, and then you pull out the scalar. You can see it, okay. So you can split the sum and then pull out the scalar. So you just you apply definition one by one to the summand one by one. To the summand meaning to all these vector one by one. Okay, so you can split them first, and then you pull pull out the scalar, split, pull out the scalar, and split. Is it clear or not? Clear? Maybe a bit abstract. So for example, let's see CV1 plus C2 V2 plus C3 V3. Okay. So what you can do is you regard C1 V1 plus C2 V2 as a vector, and then you can split this two by the definition. And you can pull out the scalar of C3. And then do the similar thing. Similar process using the property, TU plus B equals to TU plus TW, TCU equals to C. Okay, so what's next? Next we will see what this matrix will do to the linear transformation. Okay, so let's look at this example here. Okay, so describe the linear transformation of x to ax using the matrix here. Okay, so let's examine algebraically what happened, right? So you take an x, take an a, take your matrix. Okay. So it doesn't tell you where the domain and codomain is. Okay, but the matrix will determine the domain and codomain. Okay, so if A is a M times N matrix, okay, then A map from Rn to Rm. So in this case, it's a 3 by 3 matrix. So this is a map from R3 to R3. Okay, so if I give you an R3 vectors, you give me back an R3 vectors. Okay, so you can see that I give you any vectors in R3, S, Y, Z. Okay, you split out to me as X, Y, and 0. Okay, so you straight away cut off the Z. So everything bring down to the XY plane. Okay, that's why we got a diagram here. So anything above or below, you don't care about the height, you just hit it to the XY plane. Okay, that's why we have this transformation here. Okay, so in this case, if we are study a sphere at the center of the origin, what happened to the sphere under this linear transformation? If there's a sphere centered at the origin, what happened under this transformation? You send all the point down to SY plane. So what do you get? Or up? Yeah. So what do you get? Can you imagine what do you get?
Got a so you like got a sphere, right? You got a sphere, okay? And then you imagine it's a sphere, not round enough, but you imagine it's a sphere, and then you make it flat. What do you get? Huh? A circle, yes.
Right, you got a circle. You get a circle centered at the origin. Okay. Yeah. Very good. Next. Okay, how about this one? So this is a 2 by 2 matrix. So it's a linear transformation from where to where? From R2 to R2. So if I give you an vector in R2, you split out vector in R2. Okay, so let's see what happens. Okay, here, if we multiply with xy, what do we get? We get Rx and Ry. Okay, so maybe not so clear what is going on here. Maybe we just pick one vector and see what is going on. Okay, we know that every vectors in R2 is spanned by 1, 0, 0, 1, right? Okay, so we can see what happens to 1, 0. 1, 0. Okay, so 1, 0 become R0. Okay, so it is initially at 1, 0. Okay, it gets sent to something R0. Okay, depend on R. Let's say R is greater than 1. Okay, so it becomes something. So I get hey, I drew something wrong, is it? Shit. So let me redraw again. Let me make it bigger. Let's look at this only. And then when it is 1, 0, it is here. If R greater than 1, then we could send up to here. Let's change the color. Okay. So you can see that if R greater than 1, it becomes longer. If R smaller, then it shrinks. Okay. You all see? Okay. So yeah. So this matrix will scale the vectors by a factor of r. Okay, that's all. Okay, and next you can see that how about this vector here? Okay, you can see that this r bit here is 1. So that means it doesn't change, but it put a 3 here. Okay, so what's happening? So let's see what happens to this calculation. So let's see, we apply to a random x1. And then what we have is the x become x plus 3y. And then y stay as y. Okay. So meaning your x change. Only s part change, but y stays. Okay. So if you look at this picture here, the lovely sheet here. So you can see that all the x change, but y stay the same. Okay, the position of y stay the same, but x change. Okay, this is what we call a shear. Okay. Yeah. And then how about if we change the diagonal bit? Okay, how about we change the diagonal bit? What happens? So let us apply to xy. And then we will get minus y and x. Okay. First of all, x and y shifted. Okay. And y become minus 1. So actually, this is a rotation. Okay, this is a rotation. Okay, you can verify this. This is a rotation. And a general rotation matrix is this. This is the general rotation matrix. About region with angle theta. So actually, this one is a theta equal to what? This is equal to 90. Okay. Okay, in general, maybe we still have a little bit more how to get linear transformation from matrix, but we will continue next time. And there are some nice picture you can look at in the textbook. You can go and try and work out. And then we will continue the last part of the matrix next tomorrow. We will go into chapter 2 tomorrow as well. Okay, see you tomorrow.
Hey.
calculate this one.
啊
calculate this one.
，OK，等一下啊，哦，等一下，你怎么 stop 了？去新的找不到。